Thanks, everyone. And thanks so much, Jody and Dennis, for organizing. So I wanted to start off with showing you guys how to follow along. So in the GitHub repo, there's two folders, 1 and 2. And we're going to start with 1. We're going to move to 2, really mixing things up. There's a README on how to install things and including Nimble, but luckily it's pretty easy because it's an R package. And so I'm going to be working off the R Markdown file and having that up. I attempted to just push everything, and in theory, the HTML should work, maybe. So it also, and that looks quite nice too. So if you double click on the HTML, it should look like a nice printout of everything, if that's your preference. But I'll just be here in R in my comfort zone. So yeah, so lovely to meet everyone. I'm Lauren Pinicio. I'm at the University of Oregon now. I was recruited up here to teach intro data science, which I'm extremely excited about. It's mostly been in Python, so I might have little moments of like, I've forgotten all my R bits, but so I was a postdoc with Perry DeValpine as a graduate student, and I was part of the Berkeley Institute for Data Science, and we spent a lot of time thinking about how to implement ecological models in creative ways and to optimize their efficiency. And one thing I realized as I was preparing for this workshop was how much smarter I was as a postdoc. So I apologize in advance for any this is an occupancy model kind of moments. But for today, we're going to focus on Nimble and particularly diving into hidden Markov models, which are models we use a lot in ecology. We're going to fit a simple dynamic occupancy model. Here's a nice little typo right there. Okay. And then we're going to dive into Nimble Ecology. So after spending a postdoc fitting all of these models and writing them all up, we had this moment where we were like, why don't we just make a package that bundles up everything that we've accomplished in terms of optimizing the efficiency for ecological models. So I also included in the GitHub repo some bonus examples, particularly quite a few Mark recapture examples, some Jolly Seaber examples, some also examples about how to write your own Nimble functions and fit your, add your own samplers and that kind of thing. So if you really want to do more Nimble fun, that's there for you. And if you're really interested in getting a deeper dive into Nimble, there is a 3-day workshop coming up in Lisbon, which sounds so lovely. And so it's on the Nimble Workshop Weebly website, and check it out. And I'm like, can I come? Lisbon? So what is Nimble? So Nimble is an acronym, and it stands for Numerical Inference for Statistical Models Using Bayesian and Likelihood Estimation. And I think during various iterations of that word, we always kind of throw in different pronouns. So, but it's kind of some of what the package is for is in there. And in general, it's a framework for hierarchical statistical models and methods. So it uses the bugs language. So if you think of WinBugs or OpenBugs or JAGs, it uses that highly used and really kind of amazing language. It has its own dialect, as Perry likes to say. So JAGs has its own bugs dialect. Nimble has its own little bugs dialect. But in general, if you're comfortable using bugs and JAGs, you will, really easily pick up Nimble. So one thing Nimble does that you cannot do in the other bugs-related languages is or some of them, is you can really easily write your own functions and distributions. There are alternative parameterizations of a lot of the distributions we know and love. So if you guys use JAGs a lot, you guys will know that you have to use tau for the normal distribution. And so Nimble tracks much more closely to R syntax. So you can use the standard deviation for denorm instead of having to do tau and that kind of thing. But that's just a little frosting. It's got a lot of additional R functionality. So it is just a package, or not just a package in R. So unlike where, when you're using JAGs, you kind of pass it over to a separate program, JAGs, and then JAGs passes it back to R. everything is done in R, which has its pluses and minuses. But a big plus is that if you're familiar with R syntax, you can like your world of programming in Nimble is already very, very broad. It is a configurable system for MCMC. So you can, if you're feeling like it would be fun, you can choose your own samplers to put on different nodes of your model. So instead of kind of having more of a black box where the program assigns them for you, you can say like, oh, no, put this kind on this node, put this kind on this node for the intention of increasing efficiency. And there's also a library of other methods. These have all been created rather recently, and but there are lots of help files on them. Again, if you're more interested in looking into Nimble, there are other workshops going on. But so it's not just a package for MCMC. There's also components for doing CAR models, so conditional autoregressive models, kind of like for spatial models. There's also a whole flavor of really specialized MCMC, like particle MCMC and reversible jump. So those are all built into Nimble already and ready for you to use. So, and another really cool thing is that you can pretty easily write your own functions in Nimble. So if there's some kind of distribution you're really interested in that isn't built in already, you can pretty quickly build it yourself. And that's all in pretty much R syntax. So it's pretty familiar to you or us. So some assumptions of this workshop is I'm assuming that you're pretty familiar with bugs in JAGs enough to be able to look at a model and be like, I understand generally what's going on, and that you're pretty familiar with occupancy statistical models. So there's been some other parts of this webinar, last webinar, that looked at multi-species models, I believe. And there's just such an incredible diverse array of amazing workshops and webinars on occupancy models and the bugs in JAGs languages and books. So my assumption is that you have some of that knowledge there, and that we're going to particularly focus on, what Nimble can do for you and what Nimble Ecology can do for you. So let's start off talking about hidden Markov models, which I think may be my favorite name for models, because it's kind of like, like a where's Waldo, like where's Markov, what's he doing? And so much of ecological models are hidden Markov models, and particularly they have latent states. So unknown latent states that are usually discrete time steps. And when we're modeling these ecological processes, we're interested in the probability of transitioning between these states at each time step. So this, in the world of occupancy models, is going from a state that's occupied to unoccupied, or occupied to staying occupied. And so we don't know this like hidden latent state. We don't know the true occupancy of a site, and we're trying to estimate it. And layered on top of the latent states, I would like to think of the observation process. So I like to think of it as a layering process. Like here's the latent state underneath that we don't see, and then like layered on top is this observational process. And that's what we actually see. And our goal is to estimate the probability of being observed in one category given the true latent state. So if the transitional probability or observational probabilities are time dependent, we call that a dynamic hidden Markov model, like dynamic occupancy model might be something you guys have heard before. So dynamic means time varying. So with hidden Markov models inside occupancy models, so the latent states are the presence or absence of a species at discrete spatial locations. Observed states are imperfect because the probability of detection is never 1, even though we always wish it would be. And we repeat samples at a spatial location to enable the estimation of the latent states. So because we have repeat samples at a place, we're assuming a closed population, and we're assuming that because we, maybe we'll see like detection, no detection, detection, we can then estimate the probability of actually seeing that species at a site given these different observational periods. Okay, so going to dig into an example from particularly using data simulations from the Carey and Schwab book. Many of you guys might be familiar with this amazing book. It uses WinBugs, but again, you can really easily transfer that to Bugs code and into Nimble code. And actually quite a few of the examples worked through are on the Nimble website. And what's really nice now is there is a package for doing simulations of these different models with it for the book. And so I'm going to use that, since I figure then you guys can go back and simulate to your heart's content and change things around. And our goal is to parameterize the rates at which a species persist in patches in which they are allowed to occur, and the rates at which species colonize patches in which they don't occur. Occupancy emerges out of the net outcome of these two processes. And my friend Lethan McGonigal uses these lovely mark release or capture figures. I always envied them. So he sent them to me, but I asked him to switch the birds to cute bees, and this is what he chose. So this is what's going on here. But imagine this is our data, and we have 3 years. And at in each year, we visit a site 3 times. And so when we have a little B in the square, that's like we have observed this species at this site. When the square is blank, that means we did not observe that species, and so on. And so when we see B, not B, B, we know this is a missed detection. Like we know the B should have been there and we missed it. And so this will help us estimate our detection probabilities. And then all the purple is where they could be missed detections, or the species might actually be absent, right? So site 6 may just be completely unoccupied, or we may have just missed it every single time. Not impossible, especially with bees. So our goal is to estimate the probabilities of all these different states. And zooming in again, so here we missed the bee, but then we observed it. So we know it was actually there. And then the next year it disappeared. So this could be instances where there was extinction at a site, or this could be, again, we just missed it all 3 times in that period and then it recolonized. So this could be extinction, then recolonization, or just persistence and we missed it. And then there are also instances where a species definitely persisted. So for example, in site 1, there were some imperfect observations, but B was there, B was there, B was there. So with these type of observations, that'll help us estimate persistence. And lastly, the last process is colonization. So here, site looked unoccupied, so the bee could have colonized and then persisted. And similarly here, so maybe the bee was there, went extinct, and then recolonized. And so these could be instances of colonization. And so our goal in this dynamic occupancy model is to estimate the probability of the latent states, so the actual occupancy of the different sites, and these 3, really central population dynamic questions. So what's the probability of persistence? What's the probability of colonization? We only need 2 because these 2 will imply the other. So we don't need to directly estimate extinction. We just need to estimate persistence, colonization, which implies extinction. And then we have to estimate our detection probabilities. So that's the core of a dynamic occupancy model. I know we're usually asking questions at the end, but Dennis, can I pause for a second and ask if everyone's kind of on the occupancy train?
Yeah, we can do that. Although it's going to be hard to get feedback. So,
okay.
Okay,
never mind.
Can type in the chat if everybody is on board and everybody's good.
Okay.
Lauren, could you make your screen just a little bit bigger, or your images?
Like that?
Yes. Great.
Okay.
Thank you.
Okay. Yes, and feel free to follow along in the Markdown yourself or on the HTML. It kind of renders much more beautifully in the HTML. I will say that. Yeah. Mixed relationship with our Markdown. Okay, so now we've all kind of ingested the dynamic occupancy model, and so here's what the equations look like, and it's kind of nifty. You can hover in our Markdown. So we usually write that the logit of phi at a site I, thinking about the next time step, we're always thinking about the next time step. Oh, psi, psi is equal to phi, so the probability of persistence, given this unknown latent state z. So this is a 0 or a 1, whether or not you're there or not. And then plus the probability that you colonize with the, the opposite of z. So let's say z is 1. So then we're just looking at the probability of persistence is all we care about for thinking about the next time step. And let's say z is 0, so a site was unoccupied. Then we're interested in the probability of recolonization. So x, the latent, z, the latent state at a site at time period k. And so if it's 1, we're interested in persistence. If it's 0, if it's not 1, we're interested in colonization. And that helps us estimate the occupancy of that site at that time point, at the next time point. And something kind of interesting that I don't think I realized until getting into Nimble is the way we write occupancy models is very based on what bugs can do, like what wind bugs can do. So we usually put the logit out here around psi. And just as an interesting note, you could also, the inverse logit exists in Nimble, so you could kind of rewrite this equation in a way that might be a little more intuitive. But I left it at the standard way that we write occupancy models, which, yeah. So that's occupancy. And then, so that's the occupancy probability at the I site in the jth year. So phi denotes the probability that a species persists, and gamma denotes the probability that a species colonizes a given site. And so this is the kind of the classic pieces of our dynamic occupancy model. So we're going to simulate the data. Let's assume we had 250 sites sampled 3 times a year for 10 years, which would be so nice to have that. We get out y. So this is what we would have observed. And so 0 is not detected and I is detected. So y is different than z. Z is our latent states, and we can actually simulate them. So z is the thing we would never really see if we were actually out collecting data, and we would actually want to infer this. But we're simulating the data, so we actually know z, which is nice. And we're going to simulate a time constant model just to keep things pretty simple. So with 3 covariates affecting our 3 different parameters of interest, phi, gamma, and the probability of detection, p. And so this uses a function from the AHM book package, which is a lot of fun. And so, make sure to run all your chunks ahead of this one. I'm going to set my seed. This is what the function looks like, where you can simulate some dynamic occupancy data. So it's sim dyn occ, and you tell it all the things you want. So you tell it how many sites, how many years, the number of surveys per year. And then I just threw in some values for the various coefficients. So with dynamic occupancy models, the first time step is always simulated a little differently because you have to start somewhere. And then after that, you're adding in colonization and persistence. So we have to have some sort of mean value for the average occupancy in the first year. Then I did not put any covariates on the first year. You guys have ever messed with these models, when you start putting covariates on that first year, things can get pretty crazy. But then we have a range for phi. So phi is not going to vary between years. Let's keep things simple. There is a coefficient for some, hypothetical environmental variable on phi, and it's equal to 1. Then I've got my range for gamma. Again, we're just using 1 value so that it's not varying between years, and my coefficient on gamma. I was trying to find some nice combinations of parameters for things to run easily. Then I've decided to make our probability of detection pretty high, so about 50%. So that means that half the time when a species is actually there, we have it's like a coin flip of whether or not we see it. And then we also have a coefficient for this environmental covariate on the probability of detection, and it is also equal to 1. And so if you guys run this, it really niftily simulates some data and plots some nice output plots of the various covariate relationships and what things look like. So for example, we're not really varying things through time. So you see our different population parameters are not varying through time. I was very impressed by this functionality. And what's really fun to do is to actually mess with these parameters and see how it affects the mixing and the efficiency of your models. I think that especially what I found is if you start really changing P, if you start making the probability of detection really, really low, it will really change your model. So for a future time, I just had so much fun with this function. So it's a lot of fun to just play with and rerun with, and I think helps build a lot of intuition about these models and what's happening when you're sampling them. Okay, so let's take a look at our data. So if we look at Z, again, this is the latent states. You see that we have all these different sites and we have these different years, and we have the true occupancy of those sites. So at first, site 1 was not occupied, and then it was colonized, and then this species went extinct, stayed extinct, recolonized, so on and so forth. This is something, again, this is the hidden part of the hidden Markov model. So this is what we don't see in real life. And so now we're going to want to fit our model. And so the Nimble workflow is a little different than what JAGs and bugs or WinBugs do, because there are more steps along the way with the possibility that you want to customize any of those steps. So usually, like say we're using JAGs, that's one of the more common packages, we would have one function where we would hand our model and everything to JAGs and it would run it. That does exist in Nimble. It's called Nimble Mcmc. So this is the name of the function. But in general, we kind of break things up into these pieces. So our first step is we're going to create our model. So we're going to write our code. We're going to give it what are called our constants that I'm going to get into how this is different than data. We're going to pass it our data and give it some initial values. Then we're going to create our MCMC. This is where you could configure the MCMC if you so choose. So you could put in the samplers you were interested in or tweak things at this stage. Then we're going to build the MCMC. We're going to compile the model. So this actually makes a C compiled model, and then we're going to run it. I'm going to be using this framework because this is the one that I think makes Nimble special in the customizability aspect. But I also, as a postdoc, I was like, but it would be so lovely for those just starting to use Nimble to just have the one function. And so if you're just getting started and you want to just take your JAGs or WinBugs models, convert them, and just run them in Nimble, you can use Nimble MCMC. Okay, so let's look at our site occupancy model. So our dynamic occupancy model. So if you guys are familiar, which I'm assuming somewhat, with occupancy models, you'll know that there's just lots of for loops in them when we're have lots of latent states. So we go for each site in 1 to n site, for each year in 1 to n year, and then we're going to model our persistence. So we have phi in a site in a specific year is equal to some intercept plus the estimated coefficient for our environmental, our simulated environmental variable, and then our actual data of that environmental variable. Then we do the same thing for gamma for colonization. So gamma for a specific site in a year, some intercept, some coefficient, our actual data. And then for the probability of detection, that's actually going to be for each site survey year, right? So these phi and gamma are year dependent, but detection happens at every survey. So we add an extra layer to our loops, and we say the probability of detection at a site year survey, and again, the intercept coefficient, fake data, simulated data. And another thing, if you did want to mix this around, I have left logit kind of on the outside here, like we usually do with occupancy models, but we could use the inverse logit and put it on the other side of the equation if we so choose. I find that a lot more intuitive. This took me a long time to get used to in terms of bugs code, but I guess now I'm acclimated, but I appreciate the ability to kind of mix things up in Nimble. So then we're going to define our ecological model. So this is the actual kind of latent states and what is governing whether or not a site is occupied. So we're going to say for a site in 1 to n site, we're going to simulate the first occupancy probability. And we just have to kind of pull this out separately because we don't have like phi and gamma from previous years. So we're saying that's a Bernoulli trial. So, it's 0, 1 with some probability. Then for the subsequent years, so from year 2 to n year, we're going to say there's some kind of occupancy, site year, and that is going to be equal to our latent state in the previous year times the probability that we persist plus 1 minus our latent state times the probability that we colonize. So this is the same, basically, you guys, what's so, I think, wonderful about bugs is this is just verbatim the equation I wrote above. So this is just, here's our X or our Z site the last year, whether or not we persisted. If Z is a 1, we're interested in this persistence probability. If Z is 0, then we're interested in this colonization probability. Then we're going to say, okay, all the sites in all the years, these are all Bernoulli trials. So that's the true ecological process that we're trying to estimate. And then we have our observational model. So we get our ecological model, and I always think of that layering. So layered on top of that is our detection process. We're going to index now, including and survey. So we're interested now in Y, so our actual detections. And we're going to say that Y for a site year survey is again our latent state, and then whether or not we detected it, right? So then our probability of detection. So if Z is a 1, we can then, did we detect it? If Z is a 0, this zeroes out. So we can't detect something that wasn't there. And then all together, so Y for a site year survey, all of those are Bernoulli trials with that probability. Then we're going to want to set up our priors. And so we need a prior on Psi1 and then a prior for each of our betas. And, if we were being very good Bayesian people, we'd probably want to put a flatter prior, but I wanted things to run quickly. So don't judge me. So go ahead and run that, and that creates a model inside of R. So we have our nice Nimble model. This is the syntax for setting up a model in Nimble. So it's Nimble code. I think in JAGS, it's like JAGS model or something like that. And then it's a parentheses and then a squiggly bracket. So everything's kind of put in there. We also have, if you guys are interested in transitioning your JAGS models and those kind of things to Nimble, we have some like how-tos on little different syntactical differences that I can point you guys to. So one of them is the squiggly bracket and then the word Nimble code. Okay. So next, we're going to set up our data, our constants, and our initial conditions. So one thing that's always fun with occupancy models is, and any hidden Markov model, is when we are sampling our latent states, we have to give it sensible initial conditions for our latent states. And so we need to, and then if you've ever had troubles with your model starting or converging, a lot of times you've given it some very unsensible latent states. So we can look at our Ys, so our observations, and we can go ahead and actually create our Zs from that. And then we want to set our zeros to NAs, because this is telling Nimble, like, hey, actually, actually estimate this node of the model, because we're not actually sure if it was there or not. It's not really a 0, right? It could actually secretly be a 1 in disguise. And so we want to have initial conditions where 1s are NAs, because we don't want to sample the 1s. So 1s are true data. We don't want to put samplers on that. It's always going to be 1. That'll be a lot of wasted computational time. So we want to say, in terms of initial conditions, anything that's real data gets an NA, and the things we actually want sampled, the Z's that are 0, should get some kind of random 0, 1. So to repeat that, because it actually might help if you run this and take a look and compare the head of Z inits and Z. I'll pull this up. So here are our Z's. Let's start with the actual latent states. And so where there's a 1, we've left a 1. This is real data. And where there was a 0, we put it in NA, because we're like, Nimble, sample this for us. We want to know what it actually is. And then for initial conditions, it's kind of the mirror image. So where there's a 1, we put an NA, because we don't need to give initial conditions to something we're not going to sample. And where there's an NA, we give it a random 0 or a 1. I think sometimes JAGS has you just give them all 1s, like as a way to, but you guys can kind of see the mirror image of this, and this is kind of a fun hidden Markov model moment, which we will, in the next section of this workshop, get rid of. So that'll be fun. So, and here's an explanation of it. So where a species is detected, 1 is provided in the data. There's no need to set up a sampler to sample this node. It will be wasted computation. The same nodes in the inits get an NA, because there's no reason to have an initial condition for something we're not sampling. And where it wasn't detected, NA is provided to tell Nimble, go ahead and sample this node, tell us what it actually is, or estimate what it actually is. Okay. So next, we're going to set up our constants. So unlike in the other bugs languages, we separate data and constants. So I'm going to scoot down a little bit to what are constants, what are data. So constants are like the indexes of your model, and they determine the actual graph of the model in Nimble. And because Nimble is going to let you manipulate these models in R and mess with them, we've separated them out. And so constants should not really change. They determine the structure of your model. Data is just your data. You could always swap out simulated data with the same model object and it would be fine, right? The actual values of the data. And so Nimble actually separates the two of them apart. So our constants are the number of sites, the number of surveys, and the number of years. Again, those are like the indexes that determine the shape of our graph. Our data is our data. So it's the Y values, it's the fake data for the environmental variables. And then our initial conditions are, this is the data values of the Z's, so that we know the NAs versus the 1s, what to sample, what not to sample. And then we have our initial conditions, and then we're just going to give it some random initial conditions for the first occupancy and for the various coefficients. Okay, so that's the dynamic occupancy model. And then the next step in Nimble is to go ahead and build our Nimble model. So we're going to give it our code for the model. We're going to give it our constants. We're going to give it data, and we're going to give it initial conditions. Both the data and the initial conditions can be set later. Make sure to run the preceding hunks. So that's, again, the part of distinguishing the things that actually determine the shape of the model, which is the model itself and the constants. And then the data and the initial conditions can be poked around with. Nimble makes this model and it gives us a little error that says that this model is not fully initiated. This gives us a little warning that tells us the model is not fully initiated, that there are some nodes that don't have initial conditions, and we can follow what Nimble tells us to and look at that. And it tells us that some values don't have initial conditions, which isn't so much of a problem, but maybe it'd be better to give them. And you can look into it. It's actually μz, and we don't really need initial conditions for that, so we can go ahead and ignore this warning message. Then we're going to configure our MCMC. So in this part, we can actually tell it what nodes to monitor. It defaults to the top level parameters. So if we wanted to monitor all of the Z's, we would tell it that here. But I've just left it kind of simple, and I've just said, okay, I'm going to configure my MCMC, and then I'm going to build it. This is also where you'd swap out the samplers if you were interested. And then Nimble tells us what samplers it decided for us. So it put just classic Metropolis Hastings random walk samplers on most of our continuous nodes, and then it put binary samplers on our Z's. So this is, all the 0, 1 nodes will just get this binary sample, and you'll see there is a lot of them. And that will come up later. So then we're going to compile our model, which always takes a little second, and then we can go ahead and run it. And I'm just going to run them both to kind of move things along. So I will keep going as these things run. I think it takes a couple minutes, but you guys will be familiar with, you can actually set here. So there is an incredible array of visualizations for MCMC, including the CODA package. And so instead of reinventing the wheel, we have just created a little toggle, and you can tell Nimble within the function run MCMC, to return me samples as a CODA MCMC. And then you can use all the plotting that CODA has for you. So there's no reason to learn anything else. And so it's running. Fun fact, the first bar always goes really, really fast, like instantaneously. And then the second bar takes the time. And the first bar is just telling you where the end is. It's not actually doing any computation. And then the second bar is the actual MCMC runnings. I was always like, ooh, it's running so fast. And then I was like, oh, right, no, the first bar doesn't mean anything. It's the second bar that's the computational stuff. And so we can plot them, we can summarize them, and just like we usually would. And one really cool thing about Nimble, so sometimes knitter gets upset because Nimble uses non-standard evaluation. And so if you're having issues with your knitter, you can comment this out and you can recompile. It seemed to be working for me. Sometimes if you clear your cache, that can, especially if you're compiling a model and then trying to rerun it, that can really upset knitter. So sometimes I clear my Nimble cache and restart. So that's just a little tip. But one really cool thing you can do in Nimble is you can manipulate your model. So you then have this model object in R that you can poke around with. And so you can use things like calculating, there it goes, calculating the likelihood of different nodes. Oh, am I frozen? No, I'm good. Okay. Calculating the likelihood of different nodes. You can ask whether something's data or not. You can check on things. And this is really, really useful for debugging. I don't know if anyone else has gotten that, those JAGs and WinBugs errors, like something about a node's parents are not initialized. And, I've lost many computers to throwing them out the window after getting that error. But here you can actually look at that node in your model and try to figure out what is the problem. So that's a really cool part. So I'm kind of breezing along because I want to get to one other part of Nimble. So you can inspect the chains like you would usually. You can see they're nice and grassy. And where's my samples? Okay, so it's still thinking about it. Or we can look at our samples like we usually do. sorry for speeding up there, but I want to get to a really interesting part of Nimble for this workshop. So that is a guided tour of kind of the basics. This is kind of using usual R code and or Bugs code for building our models. And the really cool thing about Nimble in terms of ecological models, I guess in my book, is that we then can write our own distributions for these functions. And we've done this in Nimble Ecology. And so basically, let me just, yes, there we go. So Nimble Ecology is a package where, so for these hidden Markov models, we have all these latent states. And we don't a lot of times really care about them, but we need to put samplers on them because we need to estimate them. However, we can actually just write the likelihoods of these different latent states and create a function in Nimble to calculate that without actually having to sample them. And so there's this package called Nimble Ecology. When we were working on optimizing the efficiency of these different ecological models, we created all of these functions for doing this, what's called marginalization. And Ben Goldstein, who's a PhD student at UC Berkeley, packaged it all up and then made all these different flavors of all of these different likelihood functions or likelihood calculating functions, and made this package called Nimble Ecology. So it provides marginalized distributions for Cormac Jolly-Sieber, occupancy, dynamic occupancy, and mixture, and basically all the hidden Markov models we know and love in ecology. And so just a quick refresher on hidden Markov models and latent states. So when we're fitting likelihoods in Bayesian statistics, this always involves calculating the likelihood of the model. So if we're in our package like unmarked, this involves optimization. And then if we're using something like Nimble or JAGS, this involves using MCMC to sample the likelihood. And so we're not directly optimizing it, we're just sort of sampling it. And we're ending up with the maximum likelihood estimate, basically. But in hidden Markov models, calculating the likelihood becomes really complicated because we want to know the likelihood of our parameters, maybe like the betas that we really want to know about, given, and so we need to include the data and the latent states. And so in the last dynamic occupancy example, we basically took a brute force approach where we put samplers on all the latent states. And then we sample from the posterior of the distribution of the parameters in the latent states. And so this can become really computationally costly. And you guys remember there was like 1,400 samplers on those latent states. And so if you have a lot of species, a lot of sites, a lot of years, sometimes it's just, it takes a day just for your model to kind of initialize. And that is a real problem. It limits research efficiency, right? I mean, how much coffee can you drink while you wait for your MCMC? And also would say limits research quality. So a lot of times it's so painful just to fit the one model that people kind of pick one and go with it. And so it constrains the range of models that can be compared. Also, all of the model assessment and a lot of the model selection has, you have to iteratively run the same model over and over and over again. And so if it takes you, 5 days to run your model, your occupancy model, you're probably not going to then do some kind of cross-validation that would take, 5 times 1,000. So we really want to increase the efficiency of these models. And so why might marginalization be helpful? And this is kind of the part that I really wanted to get to of this workshop, because I think it will be so useful for so many people. So we can sample the likelihood without sampling the specific latent states if we calculate and integrate over all possible values of each latent state. This means writing a likelihood function that considers all the possible latent states and computes the likelihood as a weighted sum across those. And so words for that are like marginalizing or also integrating out, I think kind of conjures the right thing in my mind. And so if you guys are interested in more of that, our paper, Pinicio et al. 2020, has a long explanation of how to do these for the different models. And then Daniel Turk, who's another core developer of Nimble, has how to do this with marker release or capture models or marker capture models. And so it's pretty amazing, the power of marginalization. So in terms of marginalization versus sampling, what are the disadvantages? Every now and then, so the winner kind of depends on the computational costs and mixing of the specific model. And we found in our paper that actually a really simple dynamic occupancy model and mixture models can often perform better with just brute force sampling. But for example, I had a really complicated multi-species, multi-season occupancy model that was just like the difference between, a day and like an hour of computational time. And you don't get these nice derived quantities. So it has become, some people report the posterior of the latent states. And so if we're not sampling the latent states, we can't calculate the posterior. So you lose your actual, you never get to see the Z's. They are just marginalized out. And so we don't get to kind of have that posterior that some people like to see. And so here are some more resources. There's the package. There's some vignettes that are very useful with Nimble Ecology, examples from the paper we did where we did all of these different optimizations for ecological models, some examples in the Turek et al. Paper. And a lot of this is based on Ben Goldstein's blog for examples in Nimble Ecology, which is extremely useful. So Nimble Ecology part is made to basically have these functions there for you. All you have to do is choose which is the right one for your model. And unfortunately, when Ben was coding these up, we realized that you need to tell Nimble what you're giving it in a function. So you need to say, like, this is a scalar, this is a vector, this is a matrix. And it's not clever enough for you to, hand it a vector and, having like a spot there for a matrix and it'd be like, oh, okay, like in R, it's like, oh, okay, this is just a vector, I can handle this. So unfortunately, because of that, we have to have all these different flavors of the different likelihood functions. And so it's D-dynamic occupancy is, for example, the function for our dynamic occupancy model. And then there are all these like 3 little post fixes. So S is for scalar, V is for vector, and M is for matrix. And so if your persistence probabilities are a scalar, then you would, it goes like persistence, then colonization, then probability detection, like we often set up our occupancy models. So if we're SSS, that means you have 3 scalars for persistence, colonization, and probability detection. We're operating in the world. So if we look at our original model, so this can be, it's not as intimidating as it might seem, because if we look at our original model, we see that for each site, and this is the key, like zoom into a site, phi is a vector, right? We care about our years. It's actually maybe even more useful to look at it up here. So phi, is for each site, like zoom into a site, we have, 1 to n year of phis. So our phis are vectors. Then we have 1 to n year of gammas. So our gammas are vectors. And then for P, we have site, year, survey. So we have for each site, year, and survey. So we have a matrix of P's. So if we start with our original model, it can be really easy to think of which likelihood, which function to use in Nimble Ecology. But, you'll hear Perry and the development team talk. It's just a bit of an, we wish it could be different, but unfortunately, this is the part of writing these functions where we have to tell it what the inputs are. Okay, so back to our dynamic occupancy model. So just gonna make sure everything ran. So I'm just gonna set up the occupancy model exactly how we did, except now we don't have to give it initial conditions for Z's, and we don't have to give it data for Z's, or data or initial conditions for Z's, because they're not part of the model anymore. So we don't have to go through the whole brain thing of like, what's zero, what's an NA, which is great. Then our model looks almost identical in terms of the top piece. But then if we look at the bottom piece, instead of having that ecological state and detection process, we're just using this one function, d dynamic occ underscore vvm, so vector for phi, vector for gamma, matrix for p. And we just hand in our psi1. So it's always psi1 is modeled separately. Our phis, our gammas, and our p's, just indexed properly. The other thing that's different is if we have different numbers of surveys in each site, we need to tell it that. And so we need to give it a start and an end for our surveys. And so I kind of set that up here in the constants. So since we have the same number of surveys in each year, I repeated the start time for 1 for each year, and I repeated the end time for the number of surveys. So this will be like 1, 1, 1, 1, 1, and this will be 3, 3, 3, 3, 3, 3. And so that if we had like different numbers, it helps with the indexing. So that's another kind of fun little switch. But I feel like this is a lot easier to read and understand. There's a lot of different examples on Nimble Ecology of how to use this. So there's that. I believe I ran that. And so then we do exactly what we did before. And we hit play and we build our model, we compile it, and we run it. And you guys will kind of notice if you run this on your own really, really quickly that it runs so much faster using marginalization. So this piece takes quite a lot less time. There is a package called Compare MCMCs that the instructions on how to install it are in the README of this workshop. And so it will actually tell you the efficiency of your different like MCMC or marginalization versus not kind of model runs. And it'll compare them and make some really nice output plots of looking at them. I didn't want to go over that in this workshop because of limited time, but kind of the dream, I'll just let that run in the background, is that you can use maybe compare MCMCs or just your kind of intuition of how long that took to run. Like sometimes it's just very obvious. Like this example, like one takes quite some time and one runs really quickly. And you can decide on the best options for your model in terms of efficiency. You can also swap out different samplers you might think will do better and check out the bonus module in this workshop for instructions on how to do that. And then you can do more than just running your model once. You could do model selection, maybe with indicator variables and reversible jump. So that's another part that's in Nimble. So WAIC is also implemented, which does involve some rerunning of the model. And you can do model assessment. Maybe soon we will have calibrated posterior predictive p-values in Nimble. That's kind of a work in process. But because you could because maybe your model takes 30 minutes to run instead of a day, you can rerun it over and over again, and then actually do some level of model assessment. So that is what I had prepared for today. Thank you guys so much. Sorry for zooming through in the end. I always feel like, when you're sitting alone running the models and it takes 2 minutes, you're just like, okay, 2 minutes where I, have a snack and in the workshop. So thanks for your patience on that. And, feel free to poke around and get everything to run and those kind of things at your leisure.
All right, thank you, Lauren. That was fantastic. There are a couple of questions here in the Poll Everywhere website. If anybody in this webinar still has questions, feel free to post them in the website. The link is here. Let me put it, polleverywhere.com EFI 2022. So I'll start reading the ones that have the most vote. So there's a question here: can the Nimble model object be reused on multiple data sets?
Yes. Yes, and that is kind of the beauty of really thinking about the constants versus the data. So the constants should, in theory, not change. So because if you're changing the constants in your model, then I do think you have to remake your model. But you could swap out different simulated data sets with the same structure. So, and you can, and if you look at the bottom of the guided tour, you can actually just swap out individual nodes if you're want to have some fun, if you're like, never mind, like, I'm going to say this whole site was occupied, if you're just playing with things, that's also a possibility.
So the compilation is done just once then, right? Because you just compile, the structure is the same, and then you apply it to different data sets.
Exactly. And so that's kind of why there's this multi-step process, because it enables you to have more flexibility. But again, if you're not interested in that, Nimble MCMC will do everything for you in one kind of usual, maybe like JAGS-like call.
Mm-hmm. There's another question here, a question for consideration after the method is shown. What if you want to model the number per site rather than whether the site is occupied?
Dennis, can you repeat that again?
Yeah, so the question, I'm also a little bit confused. What if you want to model the number per site rather than whether the site is occupied?
Like the abundance, so an N mixture model. So yes, and so you could, for example, instead of basically with the latent states, we have a binomial, and with the observational process, we have another binomial. You could throw in a Poisson or a negative binomial, what have you, kind of, and have an N mixture model. That is also a hidden Markov model. I will warn that they are very computationally intensive. It's a lot of difficult summations. We did find that brute force sampling of the latent states often perform better in those situations, though the development team is working on some other ways to marginalize those particular functions that would speed up computational efficiency. So yes, those are possibilities.
Mm-hmm. Great. And then there's a question, is there a built-in Nimble function to look at model fit? Compare our observed data to the expected data based on the model posterior distributions, or a way to predict using new data?
So
yeah, I guess the question is, when assessing model fit, what are the functions that are available?
And so soon, we will have calibrated posterior predictive p-values. And so if you guys are familiar with those, so there's this world of posterior predicted p-values, but then there's been some papers showing that they often aren't doing what you would hope they would be doing. And so there was other papers proposing a calibration to ensure that your distribution of posterior predicted p-values were what they should be. And so that process involves iteratively refitting the model. So that should be in there soon. We do have WAIC for model selection. It's kind of the classic. You just have to have a toggle on when you use the run MCMC. You say, like, I think it's calc WAIC equals true. And one really key thing, if you are sampling your latent states, you want to make sure you're monitoring all of them so that is going into your WAIC calculation. Because otherwise, if you kind of like change your simulated data or mess with or if all the things you monitor go into your calculation of WAIC, and so if that should include your latent states. I'll just say that. And so that is a kind of a little nuance. You don't have to worry about that, of course, if you're marginalizing, because you're not actually sampling them. But it's an easy toggle. And one could also imagine, I think indicator variables are often used in Bayesian statistics. And so without reversible jump, that can be tricky because you can get stuck in weird likelihood spaces, and it's hard for you to jump back on a parameter value. So like, if your indicator variable is set to 0, the value of kind of your like covariate might end up somewhere odd, and then it's really hard to kind of go back to a more reasonable likelihood space. And so reversible jump enables you to do that. And so if you're interested in model selection that way, you can use reversible jump, which is really cool. Yeah, so those are all the pieces. I imagine I might be forgetting one, but I think that I spent a lot of my postdoc trying to write the CPPP function, as we always would like to add as many P's as we were feeling on that day. And it was interesting to try to implement, because a really core part of it is you needed to have your MCMC pretty darned efficient to be able to to be able to calculate these, let's say, rerun your model 10,000 times, And so that's, in the end, we took 5 steps back and started thinking about how do we write marginalization functions for all of these different models. And now the team's getting back to getting that to work.
Yeah, and I think one thing that was still part of the same question was really if there's a way to predict using new data. So what I'm thinking is like GAMS or LM or whatever that you fit, and you just put predict and it comes out. Is there any functionality like that in Nimble?
I imagine if you were clever about it, yes. I think particularly where you can, after running your model, so you can simulate data from your model, which is kind of what predict is doing based on the values of your parameters. So yes, and I will ask Perry to write something up and post it more on that piece. I have not used that piece of Nimble, so I'm a little less nimble about it. Yes, my postdoc was full of Nimble puns. Yeah.
All right. There's a question here. I've dabbled with making my own functions, but often get hung up on defining scalar versus vector outputs when in loops. Do you have some tips on that?
Yes. And especially when I was preparing this workshop, I was trying to think to myself, because with the simple occupancy models, not the dynamic, there's only 2 versions of the function. And so it are the marginalization functions, which I think this question is referring to. Yes. And so it can be nice to start with the simple models, and you can actually check. I think I have this up on I had pulled this up. So if you look at the Nimble Ecology package, which of course is on GitHub, there are test cases for all of the different functions. So for example, if I look for VVM, and it kind of shows you what things should look like, if that's helpful. So this is a test case that works. So you can look at, okay, there's a probability persistence. This is how it's indexed. This is how probability colonization should be indexed. And just looking at the indexing in the working examples is really helpful. But also, starting from the really basic occupancy models and working your way up. That's how I often approach the occupancy models. Okay, can I get it to work on this simple example? Maybe with 3 scalars, and then I'm going to take 1 step up, and then I'm going to take 1 step up. And that's another fun thing to do with the package for simulating the data, and something I hope we're able to recruit either a really amazing undergraduate or whoever is feeling like it is creating examples for each type. These are helpful, but ones that are actually based on the simulated data from the population book. But yeah, so I guess take homes, starting with simple models and working your way up, looking at the GitHub repo of the test cases that are working. And then sometimes also what I did is thinking of the way I'm still a little bit more comfortable thinking in the way I would think with JAGs or WinBugs, since that's been around for so many years. And so I write that model, and then I look at the indexing I intuitively did there, and I just convert it over. But I'm hoping we have more examples soon. Yeah.
All right, so one question here is, thanks for the great tutorial. I'm wondering if Nimble has built-in functionality for exploring and summarizing results. For example, pulling out coefficient estimates for slope parameters, getting estimates of occupancy over time, etc.
Yeah, so there is a summary. Let's see, there it is. So like the output of JAGs or WinBugs, we have our means and our different quantiles. So you can easily pull this out like you'd pull out pieces of a matrix. And depending on what you wanted tracked, this would look different. So these are our top level parameters, like these are our slopes and intercepts, and then our estimate of psi1. And so if you wanted all your Z's, I did not monitor the Z's because there's just a lot of them in this model. I did not, even when we were sampling them, I did not put a monitor on them. And but those would be outputted as well. And you could explore them just like you would in JAGs or WinBugs.
Well, one of the things I'm noticing here is usually on the JAGs output, you see our hat, and assuming you ran multiple chains, can you run multiple chains within Nimble?
Yes, and I ran 3. Yes, just because that's a yes. So then we can look at the nice mixing and things like that. So I think, I think there's some controversy around our hat, and I think that Perry might have more of a digression, Perry DeValpine, on why our hats are not included. But the hope is that you could do more, right? You could look at the grassness of your chains and be like, which I love that terminology, and be like, okay, that looks pretty good. And then you would actually do some model assessment and model selection because of the increased computational efficiency. And so, yeah.
Yeah, but it's not included as default, right, on the when you show the summary.
I think you could make it, but not by default. It's kind of like a little piece of opinion by the creators.
Yeah. There's a question. I'm newer to these models. What sorts of crazy things happen if you put covariates on the first year?
Oh, I have found that convergence is so much harder. And and so for this, I mean, of course, which is also interesting to think about, like what we can actually, what is identifiable. But if you start putting covariates on the first year, and we don't have a lot of information in that first year, right? Like we don't have colonization and persistence kind of informing things. And so it often will just take a lot longer to mix. So like getting first, like this, depending on this parameter, this sort of like washes over all the other parameters of the model. And I guess it's how I think about it in my mind. I hope it's accurate. And so a lot of times, if you want just a simple model to run quickly, you don't want to mess with that first year because it'll just take a lot longer to mix. Which, of course, if that is your ecological model and you have a reason for thinking you need covariates on that, then you need to make it work. And maybe it'll just take longer to run and those kind of things. But because there's such more of a probability space to explore, I guess, in my head. But I was kind of like, and it's so much fun to do. I actually think that just simulating the data and messing with it and then looking at run times, maybe using, like seeing how long things take, especially, let's see, we're like tweaking, scrolling all the way up to where I simulated the data, like, yeah, tweaking all these different things and gaining an intuition for how this changes like the model graph, like maybe making actually phi be time dependent, and like what that does to estimation thing is just a lot of fun. Like, and I love the ability to be able to simulate the data and just kind of like gain intuition for it. So it's my little, and if it doesn't take you right, and if you're do this with the marginalized one, because it's a lot faster. And so if you're not taking days to run things, you can actually do that.
Mm-hmm.
So,
yeah. There's a question. If you want to run if you want your run code to use a function not defined in the Nimble language, what do? So the example that this person is giving is, I have a model where I want to use a fast Fourier transform.
Yes. So, and in the bonus modules, there is one about kind of like writing your own distributions. And so you can really easily define your own Nimble function and just tell it what kind of inputs you're giving, write the equation, and it's all gonna be R syntax, which is lovely, right? So if you are, it's not, you don't have to learn a new language to do it. And then you just kind of load it in to Nimble like you just register it. And then it's a function in Nimble. There is also, an incredible array of functions in Nimble. So definitely look at the rather large handbook and make sure yours already isn't there. And my brain is not quite like, I haven't stared at that in a long time, but I'm almost like, I think we might have that one. So maybe.
And there's a question here that's, are there any situations in which JAGs may perform better than Nimble? I'm interested in switching from using JAGs to Nimble, and I was wondering when it might be advantageous to use one versus the other.
Yeah, and definitely take a look at our 2020 paper that is called One Size Does Not Fit All. And there's some links in, let's see, I think in here, I'm just going to do something rather nauseating and scroll really fast. Okay, so we compared quite a few different models, this one right here, and we ran it in JAGs. JAGs samplers implemented in Nimble, and then a whole variety of different Nimble flavors is how I'd always think about it, like vanilla Nimble, like what Nimble will do by default, and then a bunch of customizations. And we did this with the models of varying hierarchical structure, and we did it with like a simple dynamic occupancy model, a multi-species model, and an mixture model. And maybe there was a fourth one. And we kind of compared and contrasted. And what was so interesting, I think Perry in particular had a lot of intuition of why things like under the hood would be working better or worse. And so JAGs uses what are called slice samplers. And slice samplers are kind of a fancier sampler, I guess would be the way to say it, than a random walk Metropolis Hastings sampler. But so every now and then that was better, like that better kind of, always taking a step, and versus Metropolis Hastings, which in certain cases just not mix as well or have as much computational efficiency. And my kind of general feeling was like the really simple models, JAGs and Nimble were either at par or JAGs could beat Nimble. And then as you gained more and more hierarchy and complexity, and then where the customization actually gained you a lot, like something like the marginalization, then Nimble would do a lot better. And so the two examples that come to my mind are, so the Turek et al. Paper has a really complex Jolly-Sieber marker capture model, and that was just orders of magnitude in computational gain. And we had a paper in Ecology Letters that with a huge like multi-season, multi-species occupancy model on bees. And without Nimble, I don't think we would have been able to really do like the model selection and model fitting that we were able to because the computational gains were so high. But yeah, so the more hierarchical, more complex models, I think you get more bang for your buck. But yeah, the really simple models, JAGs and Nimble are pretty interchangeable.
And
so
can you say anything about a comparison with STEM as well?
Yes. So, and particularly with occupancy models, my understanding is that you need kind of a workaround to deal with the latent states. So Stan, to get it to run, like there's this like little like workaround you have to do to deal with the latent states. And so we didn't compare with Stan just because we'd have to like write the models in really different ways. And so that adds this layer of higher complexity. I know that Nimble is implementing soon the Hamiltonian kind of way of sampling, and so that will also be built in. That is the big gain, right? Is their way of doing the sampling. So soon Nimble will also have that, but I don't know much. I'm not quite as well versed. I know that if I'm just doing a very simple mixed model, I often use BRMS, like I, use, luckily they all have similar syntax, so you can kind of pick and choose.
All right, yeah, so last question that I have here is, I'm new to the whole thing. What was the need to break up the full model again into an observation and a process model?
Yeah, so imagine, in ecology, we're going out, we're sampling something, let's say bees. And a lot of times, if we had infinite sampling effort, we might actually be able to perfectly observe those species. But most of the time, we often miss them. And what's so interesting is this even happens with plants, right? So if perhaps the plants are in a state that's much more difficult to identify, like it's not flowering, like even though it's actually there, we're missing it. And so we then have this layer process, right? We have the data we actually collect, which we know is not perfect. Those zeros might really be ones, right? Like those misses might be the species is really there, we missed it. And so by sampling a single site multiple times in a season, assuming that each time we go, like the species is either there or not, and we're just like re-observing what's going on, we can estimate the probability of detection. And then underneath it is what we really care about, the latent state, the true occupancy. And there is just, I kind of zoomed through that piece because there are just some amazing, amazing books on occupancy modeling, particularly the book that the simulation's based on, the Bayesian population analysis book by Karen Schwab, I think. And so that one's incredible. There's also a new like multi-volume series that I really love. I think Carrie's also involved in that one. And so I highly recommend those books. They have great worked examples. All their code is online. There's like a Winbugs version and JAGS version, and we have a bunch of Nimble ones as well. And so, yeah, for getting familiar with occupancy models, those are really helpful places to start. And then sometimes I think it's really nice to have a physical book next to you, to like circle and highlight.
All right, great. So we are already at 1:30. Lauren, thank you very much. This was fantastic. I think it's going to be a great resource for anybody that wants to get into Nimble and start working with these models.